the
here
far door
all
there?
day.
Tim,
What's
can you
that?
come in at the far door? Because I can let her in.
Yeah, that'd be great. So, or I'll just give time to pause. Hey, everybody, welcome back. Welcome to session 4.
Woo-hoo.
And did everybody get their attendance thing filled in? Cool. I'm gonna go ahead and just go past this. All right. So before we get started here, I do want to take a few minutes to talk briefly about the employee and employee tester. Just to kind of go over that. I know a lot of you had a chance to check that out, and I kind of want to go to the answer again because it's not test. You're not being evaluated on this, but just to see if this is the way you might have approached it. Same idea. So you had to fill in the code for the constructor. We know that the purpose of the constructor is to initialize our instance variables. Last week we learned all about the anatomy of a class, right? So we looked at what a class was, the instance variables, the methods, and our instance variables here for our employee class was our first name, last name, and salary. So we had those 3 instance variables. We had parameters that we used to initialize the instance variables with. Where do those parameters get values? When I construct the object over in my other class, in my tester. That's where I provide those values when I make those objects. And remember, what is a class? Think about when we talked about the cars or the house, where we had, we could create 75 different houses all with the same blueprint. Different color, different address, different, roof tile, whatever it is. But they're all the same blueprint. And those attributes, house color, house address, would be instance variables that I'm setting here. We didn't look at the code back then, but we just looked at the concept. Well, here I've got my first, last, and salary, which I use to initialize my instance variables. Get initials, the first letter of the first name was first name substring 01. The first letter of the last name substring 01. That's a callback to the string manipulation that we did before. Get weekly salary. We calculated it and then I returned it. Could you have just returned this calculation? Yes, and it would have evaluated it. And if you did 52 instead of weeks per year, totally fine. Just provided a constant up here. But if you said 52, the reason we have constants is so that someone else reading your code doesn't go, where did that 52 come from? Oh, it's the weeks per year. It's much more obvious, right? And then but I could have just said return this and done it in one line and it would have been fine. These 2 are my accessor methods. They give me some information. They don't change the object at all, right? It just said, I've got this employee now, but has a first name, last name, and salary. What are his initials or her initials? There we go. It's the first letters. What is their salary? Oh, here's their weekly salary. Then I had a mutator method. By the way, the accessor method told me what it returned. It returned a string, returned a double. A mutator method, or a modifier method, they're also called, modified my object. Oh, now I have a new salary. I gave the employee a raise, and they have a new salary, and I've modified one of my instance variables. And then here is another accessor method where I just simply return my annual salary. And if you remember, this is what it looked like originally, the JB weekly salary, and then I went to bank account tester, employee tester, and we had this, right? We had and mine says employee key because this was the original, or this is the key here. Yours just said new employee. But I had James Bond and 104,000, right? And that's where we got their initials, we got their weekly salary, we gave the employee Agent 007 a raise, and then they now have a new salary. And then it says now create another object. So I created an object, Tim Gallagher. I have an annual salary of $10. Doesn't it feel like that sometimes? And then I print my initials and my weekly salary, and then I gave myself a 400% raise because, by gosh, why not? And then print my initials and salary. And the point of doing this was to just reiterate, I have one class, and it worked for James Bond, and then it's also going to work for me, and it's going to work for every other salary, because I'm just providing a name, providing a salary, and then that object has its own attributes. And each object has its own entity with its own instance variables and its own set of the methods. So if I change one person's salary, everyone's salary doesn't get changed. So when I run this now, and up here, and I say run, it says that James Bond doesn't change, right? JB weekly, JB new salary. TG weekly, 19 cents a week. There you go. And then, but then I got a new salary up to my 400% increase. Well, that was already in decimal form, so that's really, yeah. So that's not 400, that's 4,000%, right? Increase.
Yeah.
So, I got $4,010.
That's a 400%.
It'd be 400%. Oh, it was already, yeah, it was in
400%.
decimal, that's right. Yeah, 400% of 10. Yep, good call. Yeah, 400, so anyway. Make sense? Cool? Good. Questions are all about last week's stuff. I know we answered a few questions on the quiz or the test. Any other particular about the module, any other test about the quiz or anything? I double, triple, quadruple checked to make sure there were no errors on the quiz this time. I did not trust my my clicking and editing again and watching answers get changed. So I double checked and triple checked, even for the ones you have coming up. So we should be good.
What was the answers to 7 and 16? I never did figure those two out.
Sure, 7 and 16. Let's look at those real quick. Wait, I just had it up. Oh, here we go. Which one's 7?
7, yeah.
7 was. Oh, this one, yeah, we were talking about this earlier too. So when we have, I went back real quick to bank account. If you remember bank account, we had 2 constructors. Remember we had a constructor with no parameters, but I still had to initialize my instance variable. I still had to set it to something, so I set it equal to 0. And then here, when I did have a parameter and I created a bank account with like 7,000, I then used that parameter to initialize my instance variable. This is what you did in the employee class. But if you remember when we looked at the bank tester, we created mom savings, that was my initial balance. College fund, that's initial balance. But then dad's checking, I didn't put any parameters, so it called the first constructor, which set my instance variable to 0. Kind of like a default if I don't give it any values. That's what number 1 is doing. So number 1, which of the following be valid implementations of a constructor? I could do it this way, where there's no parameters, I just set my temperature to 0. Not really useful, and we were talking about how that's not usually an option professionally. Most companies say you can't have default constructors. Make sure it's explicit every time. Here's an explicit parameter that I'm using to initialize temperature. That's a good valid way. And then this one down here, I'm trying to call new temperature when temperature is just an instance variable. It's not an object. That doesn't work. So the answer is 1 and 2. And that's why 1 works. And then what was the other one?
16.
16. So this is one where, again, this was tricky. I want to see if my mileage is more than max miles. So here's a good one. If mileage is greater than max miles, return true, else return false. I'm returning a Boolean, so I need to return true or false. This one doesn't work, because this one says if max miles is true, well, max miles is a number, it can't be true. And I certainly don't want to return the max mileage, because it's a Boolean method. But this one here, this evaluates to true or false, right? Is mileage greater than max mileage? That's true or false. So this is going to return whatever this evaluates to. This is basically a shortcut for this, only because it's returning a Boolean, which is a true or false value. So this is saying, hey, if this is true, return true. If this is false, return false.
Right.
Well, how about just return this? Whatever this is, whatever this evaluates to, return it. Because it's a Boolean expression, and I'm looking to return a Boolean value. So that's why that works.
And why is 3 wrong?
I can't compare a mileage to true. I can't return max miles because it's a number, and I'm supposed to return true or false. This says return a number. Again, I'm supposed to return true or false.
Okay.
These are trying to return numbers, and this is trying to compare to number true. It's like, hey, is 50,000 or is 200,000 true? No, it's a number. It's not true or false. I could say, is mileage greater than max mileage? And I could say, if mileage greater than max mileage, double equal sign true. That's a longer way, but I really don't need that. I just want to know if this is true, right? So these two both work. Good call. Others here? Okay. Continuing on, 2 things that we're going to be covering today are Java stuff we'll get to a little bit later. That's where we're getting into arrays, which is something called a data structure. And those are fun. But before those, we have two non-Java topics that we're going to cover today. And there. We're going to cover two things. We're going to cover sorting algorithms, which are just, again, algorithms, ways of producing the desired results, right? Things like that. And we're also going to cover what we call is big O notation, which is not as risque as it sounds. And just leave it at that, because with high school students, that ends up being, can be a topic. Actually, most that even just that goes over most high schoolers' head, which is good. But I want to talk about sorting algorithms first. And now these are not going to be Java specific. I have a bunch of things that I want to put them in order. And I'm actually doing this before we talk about arrays. Arrays are groups of data or lists of data in order. But I don't want to even talk about those yet. I want to talk about what I can do with a bunch of data, because this is not Java specific. These are just algorithms. These are how do we order things, how do we put things in order. A sorting algorithm is used to reorder a group of items in order. How do we put them in order? Decreasing, increasing, alphabetical, by color, by height, by shoe size, whatever. We can put things in order. There's lots of different types of algorithms, and each has its own strengths and weaknesses here. So we're going to talk about different types of algorithms and how they work, and we have some cool little videos to go along with it as well. And then once we get the idea of an array, you'll get the idea of there it goes, plan. So and you'll see how we'll actually do this in Java. So the first type of sorting algorithm is something called a bubble sort. This is one of the worst sorting algorithms. It takes forever. It's the idea that you just have a whole bunch of numbers, you compare them. Whichever one's big, if you take the bigger of the two, you move it to the right. So here, like, did you know 6 and 8 didn't swap, and here 8 and 7 is 8's bigger. So I'm going to move 8 to the right. Now let's compare 8 and 2. 8's bigger, so I'm going to move 8 to the right. Come on. There we go. And then I'm going to compare 8 and 4. 8's bigger, so I'm going to move that to the right. So now, what do I got? I got the biggest number at the end. Great, now I'm going to go all the way back to the beginning and do the same thing again. 5 and 3, which one's bigger? 5, so I'm going to swap those. 5 and 1, which one's bigger? 5, so I'm going to swap those. 5 and 6, which one's bigger? 6, so I'm not going to swap it. So I'm going to 6 and 7, which is bigger? 7, not going to swap it. But then 7 and 2, and you see by getting the bigger one each time, what's happening? Now 7's going to be the next number at the end, right? And 8's locked in. So 7 and 4, swap. And now 8's locked in. And this works. Now go back to the beginning. I'm going to keep doing this until eventually I'll get them all. Will this work every time? Sure. Will this work if I have 100,000 values in order? Yes.
But it's going to take forever.
It takes forever. So when we talk about doing this for a handful of numbers, it works no problem. This is the most ineffective because I keep comparing, swap, comparing, swap, comparing, swap. It takes forever. This is the least efficient, but it's the easiest one to get right because, you know, a trained monkey can do it, right? Find the bigger, find the bigger, find the bigger, find the bigger, go. Find the bigger, find the bigger. Okay, here's one. That's called the bubble sort. Another one that's a little bit better is called the selection sort. What this does is, this one's moving faster. This says find the smallest, put it first, find the next smallest, put it second, find the next smallest, put it third. And when I say put it third, it's going to swap to whatever is in that place. I'll show you. So yeah, this keeps running here. So it says find the smallest. So it thinks 2's the smallest. No, 1's the smallest. Put it next. 2's the smallest. Yep, swap this up. What's the smallest? 3. Swap 3 and 6. See a little black arrow? I'm going to show you another animation of this. But the selection sort is named because it says we find the smallest one and then we swap. We find the next smallest one and we swap. This is actually faster than bubble sort, right? This works. Am I still recording? Yes, good. This finds the next smallest and swaps, the next smallest and swaps all the way down. This is called selection sort. I'm selecting the smallest and I'm moving it to the front. Find the next smallest, move to the front. This is a lot quicker than trying to do this swap, 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 which the largest number bubbles up to the end of the list. That's why it's called the bubble sort. But notice, this isn't going to do a swap until I find that smallest one, and then it just does one swap, right? That's the selection sort. Another one, now, the problem with this is, what if it's already in order? it doesn't know it's in order, but what does it have to do? It still goes all the way through, finds the smallest, and swaps with itself. Finds the next smallest one. So even if it's sorted or close to being sorted, it has no way of knowing that because of the way the algorithm works, right? Here's one that's a little bit better. This one's called the insertion sort. It's called the Scootin algorithm. What this does is it says, okay, 6 is good, 5. 5 goes before 6. Let's scoot 6 down. Okay, now 5 and 6 are good. Take the next one, 3. What am I going to do here? Oh, I'm going to scoot 6 down, scoot 5 down, and now 3. Now notice, I'm building a sorted list. There's other ones that are smaller. I'm going to be scooting stuff down. Right, 1, I got to scoot down, scoot down, scoot down. There we go. 8. I don't have to scoot anything down, so it's good. 7. Oh, I only got to scoot one thing down, right? I got to scoot the 8 down, and then we're good. And now the 2. Well, I'm going to scoot a lot of them down, right? But the idea with an insertion sort, it doesn't look for the smallest. It doesn't go to the end every time. It just says, take the next one, scoot things down, put it in place. Take the next one, scoot things down as I need to put in place. I'm building my sorted list, just like the selection sort is, but I'm building it not by finding the smallest, but just by taking the next one and putting it where it needs to go. Advantage, if it's almost sorted, it goes, hey, oh, this one's at the end. Oh, no, I don't have to, oh, and there's no scooting going on, right? If it's already in order or close, there's very little scooting happen or shifting. It's technically shifting, not scooting letter. But, so that actually makes it a little bit more efficient, especially now. What if the list was completely backwards? Well, then you're really not saving anything else. It's pretty much just as bad as selection sort because it has to go through and scoot everything every time, right? That's my insertion sort.
I feel like that's the algorithm I use when I'm alphabetizing my papers
Sure.
to pass back.
Yeah, you have a couple in order. You're
Yeah.
like, okay, the next one goes here. Oh, the next
Yeah.
one. Yeah, it's kind of the idea. Now, that's great. The last one is, now, so this is, all 3 of those work well, right? Except, what if I said, I tell my students, I lock you in a room with 100,000 exams. I say, put them in order, or put them in order numerically by student ID. What do? You are not going to say, okay, where's the smallest?
No.
And then put it first. And then, okay, and you're not going to, the scooting thing works at first, because I got 2, now I got 3, now I got 4. But then you're like, oh, exam number 524,612, right? Or, well, I guess that wasn't a million, it was only 100,000. So exam number 52,512, scoot, 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 scoot. Oh, it goes right here, right? So later on, that whole scooting method becomes just as problematic. What would you do?
I'm gonna break it up into
Break it
smaller
up,
categories.
right? And then what would you do? You break it up, but they're not sorted, you just broke them up, But then what?
Then you sort those.
You sort those. How would you sort those? By breaking them up into smaller categories. How would you now sort the 10,000? Break it up into 5 and 5,000. Would you? And here's even better. So what if I told students, what if I pay you $1 million to sort this 100,000 exams? What would you do? I'd be locked in there for a week. No,
No,
you
I
call
hired someone to do it for me.
You call 2 friends. You say, hey, I'm going to give you 400,000 to sort this 50,000 exams, and 400,000 to sort this. Now, what do? When those 2 are sorted, though, you still have to do what? You got to put them together. So you got to merge them. Well, merging is not too bad. If you had 2 stacks of things that were in order, you say, okay, take this one, 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 right? And just kind of put them together. That's easy. That's a merge. That's actually called the merge sort. The merge sort takes this and divides it in half, divides it in half, divides it in half. And where do we stop? Well, when we're down to 1, when you're down to I tell the kids, you split up into 100, split up into 50 and 50, 25. Eventually you have 2. And what do you do with the 2? And you're paying the kid, okay, I'm going to give you a dime to sort this one and a dime to sort that one, and I kept the 50 cents that I got paid to sort 2. And then you're like, it's sorted because it's only 1, right? It's done. Then you merge those 2, and then they merge them. Now they're merging here, so they're merging the 3 and then the 5 and the 6. So now that half is merged. So now the other 2, what do we do here? We're gonna. Did they split those yet? Oh, now they're merging those. And then the 2, and then the 7, and then the 8. And now we're going to merge these 2 sorted lists, right? And then we have the one, and how do you compare the fronts, right? So 2, 3 to 4, oh, 3 comes next. 4 to 5, 4 comes next, right? And this it's not really that effective when there's only 8 numbers, but this is how you would approach something when there's a lot. This is actually what we call a recursive algorithm. It's a divide and conquer, the idea of hiring somebody, creating a clone. You don't need to get into recursion for the test, but that's something that works out really well. I have some other, these are okay, but I've got some better animations to show you. And these are in eCampus. If you go to module 4 under, no, it's not IB.
I was like, that's not our logo.
I'm just, it's been a week. It's only Monday. Module 3, no, module 4, visualization links. You want to play around with these. So visual sorting blocks. So this is a good one. This takes, it's a little bit, there's the instructions. You say create, I'm going to actually do a little bit larger. I'm going to do something like, let's do 30 random. So here's 30 random numbers or sizes, right? Now I'm going to sort them. I'm going to select bubble sort. And you can see what, it kind of gives you like some code here. We don't need to worry about that just yet. But this is that swap, right? See how it's comparing and changing? That's the bubble sort. I'm going to speed this up. But you can see even when I speed it up and that top one is getting swap all the way to the end. And now, right, the larger one, whoa.
That wasn't nice.
I don't like that. Here we go. That was weird. It just switched to it. I think I was timing out of that one. But here is, yeah, it's swapping the largest, right? What it thinks is the largest all the way there. And this is bubble sort, right? The largest all the way to the end. That's going to take forever, and that's the highest speed it goes. I'm not going to keep going. So let's look at selection sort. Selection sort does this. Now this is a little bit quicker, right? Find the smallest, and then it swaps. Find the next smallest, right? And then swaps. Find the next one, and it's cheating here. Hold on, it's the graphics are getting ahead of it. I'm reloading it. Selection sort. Let's do. We can see the numbers here. This might be a little bit quicker to. See, it finds the smallest. Oh no, 12 is the smallest. Oh, still 12. Oh no, 6 is the smallest. So what does it do? It now takes 6 and 40 and changes them. Now it's going to find the next smallest, which is going to be 6 again, right? But let's speed this up.
And orange means it's like locked.
It's locked in, yeah. And if I do that, speed it up.
And
now
so
you
the
can
red
see.
is like the memory.
Correct. The whole thing is in memory. Yeah, the whole,
But
all
like
of it
it's
is.
remembering that, okay, so far this one's the smallest.
Right.
Until I find
another smallest, that becomes. So selection sort was a little bit quicker, right? Let's look at insertion sort. Remember, insertion sort is the scooting, right? Let's go ahead and I'm going to put this up to 30 again. Actually, I think the highest I can go is 43. So let me do that. That's what it fits on here. So if I do sort, this is the insertion sort. This is where I'm scooting things down. Oh, it's actually going to pull it out here and push it back in. So you can see the scooting right there. Yeah, and it doesn't need to scoot. So the first one's not a lot of scooting going on. And if you'll notice, as we speed up, early on, it looks like this is moving really quick, right? But then as we get further along, this gets really slow because there's so much scooting going on, right? So this one, my insertion sort, and again, this is me just going over them again just to get them locked in your head. We did bubble sort, we did selection sort, but now we're doing insertion sort. This is where we're doing all the scooting, right? Takes the next one, puts it in place. In order to do that, it's got to compare all the way down, right? And you can see how much longer it's taking as I go through. Let's speed it up all the way to the end here. 7 times the speed. Even at that speed, it's still taking a while, right? Now, I said insertion sort. Do we need the satisfaction of watching it finish?
Yeah.
Okay. All right,
You gotta go let Kylie in anyway.
Yeah, is she here yet? She's not here yet, is she?
I don't
No,
know.
about 35, yeah.
She texted
So we'll do a second.
It's like watching golf.
Yeah, pretty much. And sorry, this is the fastest I got. And of course, there's a couple small ones down there, so it's going to do a lot of scooting. But this is the insertion sort.
It's in the hole.
He steps up to the green. Bangs left. Pulls out. It's 5. I have golf. But you can see now, so now selection sort looks slow at first, but then as it got closer to the end, there's less to search for, right? So selection sort speeds up, this one slows down. Since we're almost there. Come on. That was like second, of course. Now this was not too bad. Still pretty. And then this last one will be about halfway, right? And then we're
It's in
done.
the hole.
All right. So if you do one that is like nearly sorted, like this, so there's not, and I do sort now with insertion sort, you can see there's not a lot of scooting going on. There's some, not yet, but this is pretty, you'll see some scooting here, right? There's some scooting right there a little bit. So this is pretty quick. But if I do selection sort when my array is nearly sorted, it's still got to find the smallest. It doesn't know it's there already. And now it's got to find the next smallest. It doesn't know it's there already, right? So the algorithm is a little bit more efficient, especially if you get to it. But now let's look at merge sort. So merge sort says, let's do we'll do it this way. Merge sort is very quick. We want to show depth, and so it's splitting in half and then merging. And the color code here is good. So it's going to merge those three now, and then it's going to take the 3 and the 3, and now merge those together to get 6. So now that array part is sorted. Now this one's going to get sorted, and I'm going to speed it up because you can see how quick it is when it gets going. Now that one's now those okay. Now it's going to merge all those. That one's sorted. Now this merge or split split merge split 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 merge those together. Now merge those together, and now I'm halfway done.
Wow.
And so this is a lot quicker, especially as you get larger, because of the split 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 merge merge merge. This is a much quicker algorithm. And like I said, remember with the insertion sort, we're like, come on, here we go. But this isn't the best. Again, just to really to make sure that we put it into your head a little more. This is okay. These are just bars. What's really great, oh, there we go, merge, 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 done, done, done. And now we've got to merge all these two together. Look at that.
That moves fast.
That's pretty cool. Because it's just merging. Merging is easy, right? Just comparing, and sort. And then here we got them in order. And you can see that's much faster. Of course, if we were like at 100,000, that type of algorithm works really well. But let's talk about, you have not seen the insertion sort until you've seen it with Romanian folk dancing.
What?
So this is like, these videos are legendary in the computer science education world here. So this is the insertion sort. Hold on.
Is it black and white?
No, it's just, oh my,
Projector.
hold on, I got it. It's just really bad color, bad lighting on the stage. What does insertion sort do? 3 and up, 0's gotta go first. Now 1.
It's kind of like a
Oh,
square
0
dance.
is the thing. Yeah, it's like a square dance type thing. So now here comes 1. 1 and 3. 1's got to scoot. Or 3's got to scoot. 1 and 0. You're done. We're good. 8. 8 and 3. No scooting left. And we keep going down. We're going to go all the way. And I'm going to speed this up a little bit. Where's that 0? 2, gotta scoot down. 2 and 3, gotta scoot down. And then, nope, no more scooting. 5.
Do you make your students do this? Because I feel like you should.
They're very amused at the video.
I just
So-
feel like you should make them do it.
Yes. I have them come up and do a few other things like recursion, which is the idea of making a clone. They pick up their clones from the crowd. But this is almost done. And then 6 and 9. Oh, 6 go down. 6 and 8. And 6 and 7. Gotta move. 6 and 5. Nope. So we're done. So now we dance. Yay! Because that's not part of the algorithm. But
I was gonna say, we're just messing up my mom.
and it goes on. I mean, they just keep dancing there now. And then there's there's a merge sort, and I like this one because Now, hold on. These are actually filmed. These are at the at Sapientia University in Romania. They make all these videos. I don't know if the dancers actually understand the algorithm, or they were just told, here's your dance moves. I don't know. I've always wondered that. Okay, so what do? They split. This is the merge sort. So what do the ladies on the right do then? Or the left? They split again. And then what do the ones on the left do? They split again. And now they merge. 2 and 4, 2 comes first. 4 and, oh, there's nothing left, so 4 comes next. And now they're done. And now these 3 are. And we're going to speed this up because even though it's fast, their dancing is slow. Split. Now there was an odd number, right? So I have 2 and 1. 1 was sorted. So now I'm going to have the 1 and the 2 sorted. 8 and 0. How's it going? What's that? Yeah, come on, yeah. How you doing? We're watching Romanian dance merge sort. This is the weirdest thing for you to walk in on. But you know. Okay, the guys are gonna sort. We don't need. We can keep going. And here they're. Oh, and now they're gonna. Here's the big merge at the end. You know. Oh, and then they pair up and they're done at the end here. And they're done. So anyway, that's our
Amusement.
Yeah.
it's again just different ways to kind of solidify the algorithms. We're good there. So we'll see some questions about what would those questions be that you'll actually see as well too. So let's continue on. So that was the first topic, was different sorting algorithms. We're going to talk about, well, how would you sort based on the fact that we just have different variables? Well, we actually have a list of variables. And then once we talk about those list algorithms, you see, oh, that sorting makes more sense. And we'll talk about that. So that was our merge sort. Let's talk about big O notation and what this is for. So again, big O notation is just, I don't know why they call it. It's a function. It's the order of an algorithm. What it actually pertains to is it's a metric that we use to measure the performance of algorithms. There's a lot that you could do with this. It kind of estimates how efficient something is. So for instance, the selection sort and the insertion sort that we saw have a certain order of or big O notation for it, but then the merge sort is a much more efficient algorithm. It's used kind of approximating the number of steps, and as the number of data items increases, how that gets measured. We don't have to know tons of it, but there is just kind of a brief overview of how this might look on the test coming up, and that's all we're going to touch with it here. So this is, it allows us to pick what is the most efficient algorithm. So for instance, here is kind of a graph. If you think of this as the origin on a math graph, this is your x versus your y. And what it looks at, the size of your input data and how much more work something increases based on the data increasing. The selection sort and the insertion sort are what we call n-squared algorithms. So as it's this right here, which is like part of a parabola, as the amount of data goes up, the amount of work you have to do increases exponentially. Right? Because it was okay. That was the insertion in the bubble and the selection sort, actually bubble sort too. All three of them are n-squared. Even though you say, insertion could be a little bit better, the reason that they're n-squared, and where it comes from, and you don't need to get this deep into it, but what n-squared means is, I have to, like selection sort, what am I doing? I'm going through the entire array, how many times? N times. So I'm going n times. Think of it as a loop inside of a loop. That's where the n-squared comes from. Even with the insertion sort, I'm looping n, and then I'm scooting. And you might say, well, you might only scoot like n divided by 2 times. We don't care about that. We just care about like the rate at which that data increases. How much does my work increase? That's kind of the idea. Merge sort, and again, you don't have to remember, is actually an n log n algorithm. And if you look at n log n, it's right here. So it's a little bit more efficient, especially as everything grows. Make sense?
Mm-hmm.
Why do we care about this?
Because of efficiency.
Yes, and I'm going to pause right here and pick up here in a minute and